semaphores. Now the semaphore is more general than a lock. So with a semaphore, you can do with a semaphore what you can do with locks and more. So I think the best way of describing what a semaphore is, or the best way of thinking of a semaphore, is to think of the semaphore as a variable, S, that counts the number of available instances of a resource. And when we say wait for S, when we say wait for S, it means that if I have at least one instance of the resource available, then I'm going to proceed and execute the rest of the code. If not, then I will be waiting. So I will be waiting while S is less than or equal to 0. S is less than or equal to 0, which means that no instances of this resource are available. As long as no instances are available, then I'm going to wait. Then when S becomes greater than 0, I will proceed. And the first thing that I will do is decrementing S. What's the point in decrementing S?
Say that you're using S.
Yeah, well, taking an instance of S. Because remember, with semaphores, a semaphore could be a binary semaphore or a counting semaphore. So the semaphore, the value of a semaphore is not necessarily 1 or 0. It could be any integer. So here, is an instance available? If yes, let me use an instance. And then access the rest of the code. And posting or signaling a semaphore is just releasing an instance of that semaphore, an instance of that resource. Okay, so yeah, S is the number of available instances of a given resource. Now you can use this to implement locks. You can use this to protect the critical section, protecting a critical section by saying initializing S to 1, and then you wait on S, critical section, post S. Now, again, the semaphore is implemented by the operating system. The process of waiting on a semaphore is guaranteed to be atomic. So again, this is a conceptual description. This is not actual code that implements a semaphore. In fact, the operating system has to do many things when it implements a semaphore. And again, a semaphore may be implemented as busy waiting or as a semaphore with a waiting queue. And we will assume by default that the semaphore is implemented using a queue. We will not assume busy waiting. We will assume, when we say semaphore, we will assume that it's implemented using a queue, which means that the process that is waiting for a semaphore will be placed in a queue, in a waiting queue for that semaphore. Okay? And we will be using post and signal interchangeably here. In some systems it's called signal. In the POSIX APIs it's called post. So post or signal, same thing. Okay, now we will see. So the semaphore can be implemented as busy waiting or with a queue. Now we will see the power of semaphores or the synchronization problems that you can solve using semaphores but cannot solve using locks. So this is a problem, the critical section problem, protecting access to shared variables, is something that you can do with semaphores, but you can do with locks as well. Because this problem is protecting shared variables. But there are other synchronization problems. A fundamentally different synchronization problem is the dependence problem, or ensuring dependence. If you have two processes, P1 and P2, And you have code in P1, S1. So this is not a semaphore. This is a code section. And a code section S2 and P2. And S2 is dependent on S1. So you don't want S2 to be executed until P1 has executed S1. Of course, remember that these are two processes running in parallel, so P1 and P2 could be different programs. So how do you ensure that the execution of S2 will not happen until P1 has completed S1? One way of solving this problem is to use semaphores. So you will have the dependent process wait on a certain semaphore, and you have the process that does has S1 signal that when it's done. So when it's done, it's going to signal it, and this is going to wait for it. Now in this case, what's the logical initial value for the semaphore? What should we initialize the semaphore? Do we want it? How many instances do we want to be available in the beginning? How many instances of the resource in the beginning? So do we want P2 to just enter the execute S2? No. Initially, we don't want it to. So we would like that value to be 0. So initially, no instance of the resource is available. And P1, after executing S1, will make an instance of the resource available. When that instance becomes available, only then can P2 execute S1. So conceptually, this is a totally different synchronization problem than protecting a critical section. So this dependence type of problem is something that you can do with semaphores, but you cannot do with locks. Okay, so that's why semaphores are more general. Okay, so the implementations, the semaphore could be implemented using busy waiting, but we will assume that it's not implemented using busy waiting. We will assume that it's implemented using a queue. So each semaphore will have a value and a pointer to next record in the list. So it will, and that's for each entry in the waiting queue. So each semaphore has a value and has a queue associated with it. So each semaphore has a value and a queue. And when the number of instances of the resource becomes, when a process does a post, it increases or increments the number of available instances. The system is going to check the queue. If the number of instances becomes 1 or greater, then the system is going to check the queue that has all the processes that are waiting for this semaphore, and it will pick one of them, and it will change the state of that process from waiting to ready. And by the way, by default, we will assume that this queue is implemented as a first in, first out queue, by default, unless we state otherwise. Okay? Now let's look at the syntax of declaring mutex locks and semaphores in pthreads on the POSIX API. It's very straightforward. So there is a data type for mutex locks, pthread mutex t, and you give it a name. The name doesn't have to be mutex. You can call it anything you want. You can call it x, y, whatever. And then you do pthread mutex initialize. You initialize it. Here it's just we're initializing it to the default values. We're not doing anything non-default. And then pthread mutex lock for locking, critical section pthread mutex lock unlock for unlocking. So you just define it, initialize it, and then you do lock and unlock. For a semaphore, there is a data type for SEMT. It's the semaphore is an extension. It's not a standard POSIX. It's not in the standard POSIX APIs, but it's a very common extension. So that's why you need to include semaphore.h. And when you initialize the semaphore, you have to give it a value. So in this case, initializing a semaphore means requires giving an initial value to that semaphore. Here we are initializing the semaphore to 1. So the initial value is this, 1. And then you do SEMWAIT and SEMPOST. So the syntax is straightforward.